So without further ado, with a huge round of applause, let's welcome our keynote speaker, Dr. Jayant Haritsa. He currently serves as a professor at IISc Bangalore.
We'll wait to get this set up. Firstly, thanks to Nikhil for an extremely warm introduction, and good morning to all of you. This is my first time at PGConf, and I must say I'm delightfully surprised. Okay? I never expected so many young people to come and listen to relational database systems. I thought it was the exclusive preserve of people like me who are on the wrong side of 50, and saying that that's something in the 20th century. Today we are doing NoSQL and other kinds of stuff, and we really don't need any more databases because they've been replaced by model-based techniques. So it's very nice to see such a, not just a large audience, but such a young audience here. Of course, some of them are my students. They had no choice. They had to come here. But the rest of you hopefully are here for this, or because the bell was rung so strongly, I think even people in the hotel who had nothing to do with PGConf have come in inside here, right? So I'm extremely happy to be here, and I would like to thank the organizing team, especially Pawan, Ashish, and Nikhil for their extremely warm invitation. And I'm delighted to be here. It's very nice to see so many database companies under one roof, and that there is so much interest going on here. So what I'll be presenting today is work that we have done over the last couple of years in our lab. And this relates to how do we use the remarkable computational and predictive power of foundation models in order to improve the performance and the functionality of traditional relational database systems. And this is joint work that has been done with master's students at IISc. This is Sriram Dharwada and Himanshu Devrani. And I started this work when I was on sabbatical at Microsoft Research a couple of years ago. So this was done with Dr. Harish Doraiswamy, who is also a former master's student of mine from IISc. So I didn't let him go. He did his PhD elsewhere, did a postdoc and came back, and we worked on this during the sabbatical and continued since then. Okay. But before I get on to the topic itself, I thought it's important that I should highlight to you. Hopefully you already know this because Pawan is the publicity chair for the ACM SIGMOD conference this year. And if you haven't heard about it, complain to him. But ACM SIGMOD Pods, which is considered the Olympics of database systems, it is the premier international conference which has research papers, it has software demos, there are thematic workshops, deep dive tutorials, provocative panels, there's a complete industry track, sponsor booths, and so on. And for the very first time, it's being held in India. SIGMOD started in 1975 in San Jose. So that's far back. Many of you won't even know that even databases exist at that time. But that was the period at which we had the relational systems coming up from the System R group at the IBM Almaden Research Center. So it started in 1975 in San Jose. And we are privileged to have it for the very first time in India, and this is in a couple of months' time. It will be in the first week of June. We are hoping it will be done just prior to the monsoon, because otherwise most of the delegates would be stuck on the outer ring road trying to get to the venue. So we hope that we will see all of you at the conference. There is also a link there, and we welcome you to register for the conference. You will really see that this is the who's who in database systems will be there, and I hope that you would be able to actually participate in the conference. Okay, I thought I should also mention, given the theme of this entire symposium, that is open source important? And actually, I would say it's very, very important. Yeah? I'm not just saying that because they invited me here, but just because in academia or in industrial research, we just say research creates knowledge. But in order to translate that knowledge into something that actually affects society and becomes a public good, that's where open source really has its prime moment. Open source, of course, spreads the methods much faster because there are lots of people who are downloading it and can quickly access it and run it. What is very important is that traditionally, lots of research that was coming out in the database conferences, including SIGMOD, VLDB, ICD, which are the premier conferences, was not reproducible. They would just present it to the conference and say, everything looks good, this works beautifully, and when you try it yourself, it was not happening. So SIGMOD also introduced what's called as a reproducibility badge, saying that you should provide both the software, that's both the code as well as the data, so that an independent body can actually test it out. And they found that often it doesn't work out very well because you are doing it under a certain artificial environment and it doesn't translate to others. So in that sense, open source makes research both inspectable and reproducible, and this is in the best traditions of science. And computer science is a little strange field. If you look in all other natural sciences like physics, chemistry, biology, and so on, reproducibility is considered the foundation. For us, it was optional, but now we have made it mandatory. Also, completely lowers entry barriers. Anybody in the world can download the open source software, then play around with it, especially students, startups, and public institutions. This is a godsend for us. And most importantly, we are not wasting time. Okay? It's not that everybody is reinventing the same wheel and going back full circle. Now you can create shared infrastructure, and therefore, I mean, like Newton said, we all stand on the giants of shoulders of giants. So we can also now basically make much faster progress in terms of having a collective improvement of the database environment. And of course, there is a lot more trust because you have a transparent surface. So now am I just saying this that in theory, but we do something as in practice? Not actually so. Our own lab, which is called the Database Systems Lab at IISc, which I started in 1995, 30 years ago. Okay? So we have several tools that have been used in many institutions worldwide, both in the academic sector as well as in the industrial labs and the industry as a whole. So we had the Picasso tool, which helped you to visualize how database query optimizers behave, or actually more accurately misbehave in real systems. That was in 2007. Then we had this interesting tool called CORD, which stands for Constructing Data-Less Databases. Okay? This sounds like heresy for a database person to say that there's no data. But we say that the best way to test a database system is without data. Okay? So that was a database testing tool that we released in open source in 2012. Then we had this plan bouquet in 2014, which was how to get robust query processing in database systems with quantitative performance guarantees. Because otherwise, as you would, most of you are actually using Postgres or any of the other database systems, know that once you submit a query, usually you have to also submit a prayer with it. Okay? Send money to Tirupati and say, please make my query run fast. Okay? But with this, we can actually give you for the first time quantitative performance guarantees saying compared to the ideal, what kind of performance can you expect? And then we had, our lab has also been doing a lot of work on the testing arena. Traditionally, this is considered boring, saying that the worst people in the company are being sent to the testing division because that's where everybody else wants to code, and these people are just doing testing. But if you are designing testing methodology, it's actually a remarkably interesting problem. All the way from traditional complexity theory all the way to actual tools that do it, there's a lot of very nice technical depth to database testing methodologies. And we had a system called Hydra, which was a database regenerator tool as to how to reproduce client database environments at vendor sites so that they can do the testing for them. And most recently, a couple of years back, we had this tool called Unmask, which says that suppose you had a database application where you only have the binary, you have lost the source code. And believe me, this is a fairly common experience. You might think, how could people lose their source code? When you had the Y2K problem in 2000, they found that 40% of the companies had either lost the source code or had not even taken it from the vendor in the first place, saying life will go on as usual. Okay? So we looked at how can you extract queries that are hidden within binaries and get the SQL out from them in a somewhat proven manner. Okay? So that way we have had several tools that are being used in the world as large. And of course, we have ourselves been a great beneficiary of Postgres. We have used Postgres in pretty much all our projects. And whatever I show you today is done on the Postgres platform. Okay, so if you just look at a very high level at the Postgres query processor, most of you know this even better than us because you have actually dealt with it in real life. So you would see that it's essentially that once the client issues the query, there's about 5 boxes that it goes through. So initially there's a parser that basically checks whether you can spell or not. Okay? And in India, spelling is often an optional feature that people have. So you check the SQL syntax and whether you put the semicolon and stuff like this. And it builds a complete parse tree. Then you have this analyzer, which basically does the name mapping. It resolves the names and the data types and builds the query tree. Subsequently, there's a rewriter, which actually applies many of this rule system transformation, especially for things like views, where you get the views being, the view reference being replaced by the actual SQL code for the view. You will also have many rules for inserts and updates and modifies and things like this. And then there's the next step, which is the most critical step, is the planner, which is the query optimizer, which searches through a very large, exponentially large space of alternatives and identifies the optimal execution plan. And if you survive all these modules, then finally you come to the executor, which takes the plan tree, basically links and loads the code for all the different operators together, and finally runs that plan. So just to give you a quick sample here, so suppose you had this query that you see on the left-hand side, which tries to return the names of employees who are working at Karnataka here and received a bonus in 2025. Okay? So you will see that there is a create view statement there about the employee view, which basically pulls out the ID, the name, and the department ID from the employees. And then there is basically a select query, which is combining the information between the employee view and the departments table, and also in the bonuses table in the nested query that you have in the exists clause. So what would happen is that after you finish the initial parser and the analyzer, it would then go to the rewriter, and what the rewriter would do is to replace the emp_view with the equivalent statement, which is the SQL statement that you see at the top, which is the view definition. But then there is the optimizer, and what is interesting here is that the optimizer now looks at how to rewrite this query. So this is a different rewriting than the rewriter that you see before, which was essentially expanding the existing macros, so to speak, that you are already there. And if you had triggers and procedures and so on, all of those are going to be inline. But here the optimizer is trying to say that, is there a better way to write this query? And if you, those of you who have used SQL a lot will know that the biggest USP of SQL is that it's a declarative language, where you only specify the goals, but not the means to achieve the goal. That is the biggest USP and also the most dangerous part of SQL, because it means that everybody can write the query in their own perverted manner. And then it is up to the database optimizer to figure out a more efficient way of answering the same query. Okay? So because you give so much flexibility and latitude, it also then means that there is a lot more responsibility on the underlying system to be able to figure out what is the more efficient way of answering the same query that you had specified in a particular manner. Okay? So if you see in this particular case, we are trying to replace the exists with a semi-join instead. Okay? And then, of course, the last step is to make the decisions about the physical plan choices as to how do you access the data. Would it be with a sequential scan or through a B-tree index or bitmaps and so on? For the joins, will you implement it with the traditional nested loops join or the hash join, sort merge, and so on? So what I'll be focusing on is not the first kind of rewriting, which is essentially expansion, inlining of existing definitions, but the second one, which is shown in red here. So hopefully, which is shown red here, which is to say that how do you take an SQL query which has been written by a developer and then convert it into something that is equivalent in terms of meaning, but is much better in terms of performance. Okay, and just to kind of make this concrete, I don't know how easy it is for you to read this, but basically this is what you see on the left-hand side is an SQL query, and all that it's doing, so I can just see the English part of this, is that it's computing the ratio of sales made in the morning, that is from 8 to 9 a.m., compared to the sales that's made in the evening, and this is between 7 to 8 p.m. Okay? And basically what you will see is that there are two segments in this query, which are almost identical because you are essentially combining this information of the morning and the evening, and you are looking at the ratio of the sales. And what you see is that there are essentially the identical query is the sub-queries are there, and one part of it talks about the morning and the other talks about the evening. That's the red box that you see in the centers of the boxes. But what you could see is that if you gave this to the PostgreSQL optimizer, and these are real numbers that I'm showing you here, it says that it will take something like 2,200 units of time in order to execute this query. But then you can go and rewrite this query to what you see on the right-hand side, where instead of having multiple sub-queries, you just have one query here, which basically does the computation of the join, and then you're using various kinds of case statements here and the where clause predicates in order to be separating out the morning sales from the evening sales. Okay? And now if you look at this second version, which is semantically identical to the first version, you ask the Postgres optimizer how much time it would expect to take to answer this query, you'll see that it comes down by essentially 50%, it comes down to around 1100 or so. Okay. Yet another example is, this comes from the ORM world, because many people don't try to directly work with relational systems. They work with object relational models like entity framework, Hibernate, and so on. And those systems allow you to program at a very high level object-oriented model of the world, but in the end, it's converted at the output to a relational model. So what you see here is the daily summary of rating metrics for highly rated blocks. That's what you see on the left-hand side. This was actually produced by one of the tools. But if you stare at it for long enough, you'll see that, and if you execute this directly on Postgres, this takes several minutes to execute, because there are multiple joins, there are various kinds of aggregations being done, and there's nesting and so on. So it looks like a fairly complicated query, okay, you look at it at first glance. But actually, you can show that you can rewrite the same query that you see on the left-hand side while maintaining semantics to something that is much, much simpler. So what you see on the right-hand side is that it's just doing a simple join of two tables, which is the join between the post table and the blocks table. And then there's a simple filter predicate in the where clause, which says that the rating should be greater than 5, which means that it's highly rated. And the rest of it is very simple. Okay? And now if you take the right-hand side query and feed it to the Postgres system, okay, and then you pray hard, it completes in a few seconds. Okay? So you see that there's a dramatic shift in the running time of the query, going from several minutes to just a few seconds. So at this point, what you would say is that, why should I even know this? I would like to write it in the style that I am most used to. I might love subqueries, or I might love set operators. You shouldn't stop me from doing that. And it's really the job of the database query optimizer to automatically have done these changes without even necessarily telling me. Okay? And in theory, this is what we teach in class, that the database system is all knowing. It will change whatever you had written. You can write it in the most natural framework for yourself, but then we'll convert it to an efficient version inside. But just like humans can get confused by the kind of formulations that we saw in the earlier slides, the database query optimizer is equally human. It also gets confused. Okay? And very rarely is it able to make this transition and say that this is a much lean, mean version of the original query. It tries to execute it in the same way that it was done before, and then you get poor performance. Okay? So even industrial strength database query optimizers, and I'm not just saying Postgres, this is true even for the commercial systems and so on, because the space is so large, because query optimization is such a complicated task. Okay? So if you look at most of the aspects of database engines, there's a consensus in the industry on most aspects. For example, if you want to do database recovery, you use the Aries algorithm. If you want to do buffer management, you use the LRU2 algorithm. If you want to do concurrency control, you use some version of two-phase locking. So there is basically people have decided that all these are solved problems, and some flavor or the other of these basic techniques would be used there. But the one place which is still a black art is the database query optimizer. And this is where you have a lot of secret sauce distinguishing between different database engines. And a few years back, you might have seen a blog. This was in the ACM Sigmod blog post. This is in April 2014, where the father of the IBM's DB2 query optimizer, famous Dr. Guy Lohmann, he had actually given a long rant. Okay? He said that even after 50 years of work on this problem, it's a mess. And he says that what is surprising is that if you get a good plan for your query, normally you will get bad plans. Okay? So we are used to in computer science usually assuming that average case will be close to best case, and occasionally, if you haven't prayed well, you will get to the worst case, which is corresponding to some pathological situations. But in database systems, it's the other way around. Average case is close to worst case. Okay? If you're lucky, you will get the best case. Okay? So that is, and there's a lot of industry use cases and war stories which kind of tell you about this. So you find that query optimization is still the last frontier. Okay? So even in industrial sense systems, there is a restricted visibility, especially on large complex queries. It needs to be able to digest it, so it breaks it down into pieces. So therefore, it misses the holistic optimization. There are many hardwired rules over a long period of time, which nobody wants to touch because they don't know how whether there will be any collateral side effects if you make changes, and you might actually run into regressions. Also, the ORM tools are notorious for producing things that are unreadable completely. Okay? So if we find it hard to read, then poor query optimizer is also susceptible to the same problems. So given this situation, which has existed for a considerable time, okay, despite many the premier companies as well as the top academic research labs all having worked on this problem, it was still largely unsolved. So we said that we know that performant rewrites can often escape your attention. Okay? Now, can we use LLMs to address this gap? Okay? So what are the challenges that we need to look at here? Firstly, what is the kind of prompting mechanisms that you need to use in order to get these performant rewrites? Secondly, is it possible for us to use LLMs to actually match human quality rewrites? Then we all are aware of that LLMs can occasionally go haywire when they're especially creative, they go into the hallucination mode and so on. How do you minimize this possibility of hallucinations? The fourth one is probably the most important, is that how do you ensure and verify that there is semantic equivalence between the original query and the rewritten version? Okay? Because the best way to do a fast executing rewrite is to drop most of the conditions in your query. In fact, that's how it happened the first time I gave some of those queries to the LLM, to ChatGPT. It said, just drop your where clause, remove the joins. It runs lightning fast. Okay? So it's very important that you have semantic equivalence and then get performance. We also know that there's often a big gap between what is promised by the optimizer and what happens in reality. Okay? What you see is not what you get. How do you minimize such regressions? This is a traditional problem in database systems, even outside of this model. And then finally, how do you produce robustness for new schemas and environments that have not already gone into the training set of the foundation model? So what I'll just do in the interest of time is just address the first couple of questions. If you're interested later on in the tea break or subsequently, I'll be happy to chat with you about the rest of the stuff. Okay, so we have a system developed in a lab which is called as LITHE, which basically signifies that this is lean and mean and agile. So it has a fairly tortured expansion, LLM-infused transformations of hefty SQL queries. And the idea here is that you start with the input query is the one that is being given by the user, and then you go into this the LITHE system itself. So initially we do some prompting to check that whether the different ways of looking at rewriting the query. What is very important is that it's also possible that not just semantic equivalence, you might also find that the LLM has forgotten to put semicolons or made syntactic errors. So we do syntax verification using the existing tools in the system. Then we look at a query costing through the optimizer to figure out whether this rewrite is at least estimated to be doing better or not. Next step is to verify whether even if it's estimating to be doing better, is it actually semantically equivalent or not to the original query? So there's a fast semantic verification module. After this, we have something which is special, which most people have not tried, which I'll talk to you about later on, is that we look at the token. So we are not just looking at the input to the LLM, we're also looking at the outputs of LLMs, and the tokens that come out from the model also have associated probabilities, and we use those probabilities to improve the rewriting quality. Finally, there's a last step which does kind of detailed checks to say whether the output rewrite that we're giving is actually semantically equivalent or not to the original. And then finally, we give this, the pink box that you see on the left-hand side, we give that to the database administrator. So firstly, it gives you the rewritten query or the transform query Q superscript T. It also tells you what is the estimated benefit by using this rewrite instead of the original query. It also tells you how this was proved to be correct, whether it's using statistical techniques or logical provable techniques. And finally, it also gives you an explanation as to why it thinks that the rewritten version should do better than the original. Okay? But ultimately, we give this to the DBA and say that, can you figure out whether you think that this would be a much better option than what you're already using? Okay, so those of you who have been following the research literature would know that you say, hey, this is just text to SQL. What's different here? Okay? And there's actually be a tsunami of papers. Okay? Pretty much every database researcher and the grandmother have been writing papers on text to SQL in recent times. Okay? And here, the nice thing about text to SQL is, if you get an incorrect output, you can always blame the user, saying that you gave an imprecise specification, you deserve it. Okay? So there's an inherent ambiguity because the textual representation will always be susceptible to multiple interpretations. And if it's not been written in a very detailed manner, it's likely that it may give you incorrect answers. But for us, the problem is much harder. We are doing a SQL to SQL transformation. It's not text to SQL. And once you're doing SQL to SQL, it means that there is a ground truth. There is a formal, provable mathematical logic that you need to essentially maintain in your rewritten query. So the logic, usually first or second order logic in SQL, has to be maintained in the output query, and you can actually say whether you did a good job or not. And there's no way that you can blame the user here because essentially the SQL query is a mathematical definition. So that's why life becomes much harder for us. Okay, so let's just look at how can we use these foundation models to do prompting. So what we started off doing was we did a calibrated study using 4 basic prompts and with increasing detail in the instructions. And we wanted to see how well does the LLM do with each of these prompts. So the first prompt is a very simple prompt, and if you can't see the box on the right-hand side, it basically says, it's very succinct. It's like, rewrite the query to improve performance. Okay, so I don't want to know more. It's like nowadays how we do coding, saying, write excellent code and just give it to me, or our students use it to do all their assignments. Okay, do something to make Jayant happy. That's a simple prompt for them, right? So this rewrite the query to improve performance is the first one. The second one is a little more detailed, and now it also appeals to the ego of the foundation models. I don't know whether you noticed, all these models are very susceptible to flattery, like some of the top politicians in the world today, right? If you say shabash to a foundation model, try it, it does much better, okay? So here we are saying you are a database expert and SQL optimizer, okay? You start off on a very high note, okay? Then you say that your role involves identifying inefficient SQL queries and converting it, and some details are given about the query, and says explicitly, please rewrite this query to improve performance while mandatorily maintaining semantic equivalence. Okay? That's prompt number 2. Prompt number 3 is that it also tells you how to go over the process. It essentially looks at the steps of human reasoning, which you see on the prompt on the right-hand side. Okay? I can share a copy of the paper and the slides with you subsequently so you can look at the details. But at the high level, this is what we are doing, giving more and more detailed instructions. And then the prompt number 4 is the same as prompt number 3, but those of you who have been using these models probably know that they like to have small inputs where they are just able to focus on that sub-problem, and then you lead them by the hand through the subsequent problems rather than throwing the entire thing and saying, go and do it for me. So the instructions of prompt 3 are provided in an iterative manner, step by step. The same instructions, but not given in a monolithic form, but in a modular form. This is also called as the chain of thought in the machine learning community. Okay, so now maybe you would say this is good enough, right? We wanted to check this out. So we took the TPC DS benchmark, which many of you will be familiar with, which has 99 queries and is a very complex decision support benchmark, which is used pretty much by the entire industry. And we just took 10 specific queries from this benchmark. And the reason that we took this 10 is that we knew a very performant rewrite by manual and visual inspection, which would do much better for this particular query. And what we did is we went and gave this to Postgres, these 10 queries, and we found that it did very little with them. Whereas if we gave them our manually rewritten version of this, there was an astounding difference in performance. Okay? So on these 10 queries, if you look at the geometric mean of the cost speedups, we usually take the geometric mean because different queries have different running times. So you take the 10th root of all the speedups multiplied with each other. It is 11.84. So there is a huge difference just in the query space. We're not touching the plans, we're not touching the optimizer, not touching the engine, nothing. Just outside we are saying that instead of writing it like Shashi Tharoor, write it in simple English. Makes a huge difference in performance, okay? Geometric mean of 12 is an astounding number. So, and here's the actual graph that shows this. Now we want to look at, so we use the GPT LLM at that time. And what you see on the graph is that on the x-axis are those 10 different queries from the benchmark. So you will see like Q6, Q11, and so on. So the queries are numbered from 1 to 99. So there is no semantic meaning to the numbers. It's just a sequence there. So you see the 10 queries on the x-axis. And on the y-axis, you see the speed up. That is, how much better is the rewrite doing as compared to the original query. And notice that this is on a log scale. Okay? So the first thing to notice is that if you look at just the basic prompt, so you see prompt 1 is the blue prompt, most of the queries it doesn't do much, but some queries it really does well. For example, if you look at query number 6, you get an improvement of almost 2 orders of magnitude just by asking the LLMs with a single sentence saying, please rewrite this so that I get better marks in my assignment. That's it. Okay? And you get improvements there. In some of the others also, if you look at, there is Q31, I think, which it does a little better and so on. Then if you look at the more detailed prompts, like prompt 2, 3, and so on, which is the orange and the green lines, they are doing significantly better on many of the queries. And then you'll see that there is a blue bar. The blue bar is an ensemble of all the other 4 prompts, saying that whichever is the best amongst the 4, let's take it up. You will see that the blue is pretty good in several of the queries. And again, remember, this is in orders of magnitude that you're improving. But if you compare it to the green, green is what the human has done. Okay? And if you ask, who are the human experts? These are our master students at IISc. Okay? They're the toppers in the GATE exam, so hopefully they know what they're doing. So this is at least the known upper bound on performance. Maybe IIT Bombay may have a different view of some of this because there are several people here from IIT Bombay. But this is what the best that we could do. And we found that if you just use these prompts, you don't reach 11.84, you reach a much more modest 3.23. But what is interesting is that although the Postgres query optimizer has been worked on for a long time, even with trivial prompting, you can jump to a factor of 3. Okay? That is what is really impressive here. But now we are greedy, okay, being humans, and say that, can I reach 11.84? Because now there is a target. Okay? So can we do better? So what we realize is that the basic prompts are fine to get you started, but they incorrectly assume that the foundation model has sufficient database knowledge. And what we did was to explicitly introduce this, and we used common practices used by DBAs, and some of you here would have been in that role already, so you know this much better than us, to basically remove redundancies in your in the query writing. Often there'll be unnecessary joins that are being computed multiple times, or to also use selectivity guided prompts. So we know that the database query optimizer is foundationally built on using metadata in the form of database catalogs, which capture the statistics of the distributions of both the data within columns as well as the correlations across columns. So we can use selectivity as also a measure to decide whether to do the rewrite or not. Okay? So here are just a sample set of rules that we used, that is R1 through R4, which basically tell you, for example, R1 says that don't do the silly mistake of repeatedly computing the same outcome. Instead, just use common table expressions to avoid this repeated stuff. Now, you might think that the query optimizer should have done this automatically, that I don't really need to tell this, but as I said, the reality is very different from the theory, and things are hard with very complex queries, so we need to explicitly state this. Then the rule number 2 basically says that try to ensure that given a table, you only scan it once and don't do it multiple times. You may often have redundant filter predicates in the where clause, where, for example, the fact that there is one predicate means that the other becomes unnecessary. So you can remove those, and also unnecessary joins. Okay? So you can see on the right-hand side that there is, again, you're appealing to the ego. You say you're a database expert in SQL optimizer, and then you actually give the rewrite rule, and you give an example of the rewrite rule. So this is like one-shot prompting. So you give one example of how this is being used, and then you actually give your user query and say, do the rewrite. Okay? So once you do this, now you see that the blue one is what you got from the prompts. The dark brown one is what you get with these additional rules. And then the green one is what is the human expert. And now you see that things have improved significantly. We jumped from 3.23 to 6.85. Okay? So we are getting there steadily. So what's the next step? Next step is, as I said, we need to look at distributions of data, because most decisions of query optimizer are a function of the quality of your cardinality and cost estimation models, which depend on the underlying statistics. So we want to augment the prompts with this information that's already present in the database system. And specifically, we focused on the selectivities of the filter and join predicates. So here, if you see on the left-hand side, there is a query which uses the exists operator, which is saying that does this particular customer exist in this subquery that you see, which is that the year should have been 1999 and there should have been order placed by the customer and so on. On the right-hand side, you see exactly the same query, but instead of using the exist operator, you are using, for Vastu reasons, you are using the in operator instead. Okay? Identical queries, there's no difference in the outcome of the semantics, but these are two different ways of writing it. And what you will see is that if there is a large instances of this customer obeying the query with the exist clause, then just using a sequential scan is very good, because as soon as you hit the first qualifying tuple in the join, you will immediately be able to short circuit it and say, yes, there's success. You don't have to go and find all versions of it. But on the flip side, if it's very rare, then the in clause is much better, because usually you'll use an index to go and find that. So if the selectivity is a low value, then in is very good. Selectivity is large, then exist works very well. So what we would say is that go and look at the statistics and decide whether to do the rewriting, that if you had exist, switch to in, or if you had in, switch to exist, and so on. So this is the rule number 5, which says that use the selectivities to decide which operator you're doing. And there are similar other rules which I've used for the prompting. Okay? Does this work? Now, if you look at this, you will see that this is the orange bar that you see now, which is the third one, which includes all these 6 rules, not just the 4 rules that we had before. So now you have brought in much more database knowledge. Firstly, knowing as to that you should not be unnecessarily repeating work that you had done. You have to try to make things as concise and lean and mean as possible. And now we're also saying that please use the statistics which are already available in the database catalogs to inform your choice of rewritings. And now you see that things have gotten much better. You see that the orange bar is close to the human bar in most of the queries. So you reach 10.57. Okay? Now we are tantalizingly close to the human performance of 11.84. Can we get there? Okay. So this is where we come to this third thing is, can you completely match the human rewrites? And something which most people don't realize is that they always complain that LLMs are hallucinating and giving the wrong answers and so on. It has often awarded me a Padma Shri. Okay? I want to send this to the government and say, please take the hint from the model and so on, but it does many mistakes. But we shouldn't be blaming the model. What is happening is that when the output tokens come from the foundation models, they also come with associated probabilities. And the probabilities tell you how confident the model is about what it's outputting. Typically, if things are above 0.9 and so on, then you know that it's pretty sure about what it's outputting and you can take it as is. But often you'll find that it may give you a probability of 0.4. And the reason that you're giving the token of 0.4 is that the other possible tokens are even less than that. It could be 0.3, 0.1, 0.05, and so on. So it is just quite confused, but it's taking the highest probability amongst the confused set. But you are not measuring that number. But actually the number comes out with it and you're not paying attention to it. So the LLMs give you a confidence probability, and if there are low probabilities, then it automatically means that this is a signal that is likely to be hallucinating. Okay? So what we do is we leverage something called as Monte Carlo tree search, okay, which is essentially a simulated tree expansion. This was already done by the programming languages folks for code generation, and you can see some earlier papers a couple of years back in this area. So we use the same techniques and said that basically the idea is that if you know that the LLM is already confused itself, don't just take it at face value and then complain saying you got a bad rewrite. Take a step back and follow multiple paths. Follow the 0.4 probability path. Follow the 0.3 path also. Follow a couple of different paths, because at the end of it, you might find that the 0.3 path is better than the 0.4. Currently, 0.4 looks better than 0.3, but it also tells you it's confused. Therefore, you follow all these paths, go to the end, look at the rewrite, and then see which is the best. And we found that in several such cases where there were hallucinations, by following the second best path. So at the current time, you think it's second best, but at the end, you find that it is faster than what was being provided to you by the 0.4 path. So essentially, you're helping the LLM explore alternate rewrites whenever it itself has low confidence. There's no point beating up on it when it knows that it's confused. So now you're exploring more of the modeling space, and you can achieve performance improvements, as I'll show you in the next slide. This is where you have the original queries on the left-hand side. You can see that it's a nested correlated query. The middle box tells you where I did not use this MCTS technique, I just used the initial prompting, you get no speed up, because all that the LLM does is to essentially move the position of the nested subquery, but it's still there. The subquery remains correlated there. Okay? It just does essentially a cosmetic rewrite. Nothing really happens. But if you look at the rightmost box, the rightmost box has essentially removed the correlation. And now look at the top, the title of that box. The speed up is by a factor of 6,500. Okay? So this is not 10% improvement, 30% improvement, and so on. This is 6,500 times. You deserve Bharat Ratna for this now. Right? This is an enormous change that you see, with a very mild difference. So what has happened is that after generating the from item I, which you see in the second box, then it has two choices, the LLM. It can either generate the where clause, which is what you see the nested correlated subquery there, or it can generate the CTE, which is the common table expression. It can go in either direction. Higher probability goes for where and lower probability for CTE. So normally you would have just taken the higher probability one and then you would have gotten no speed up at all. But if you took the mildly lower probability version, which is the CTE, now you see that you come up smelling like roses, you get a 6,500 times speed up. So the MCTS exploits the low confidence of the LLM to say that, let me do a wider search, because this is uncertain ground. I need to try many things. Okay? So it's like the Google Maps. If you are unsure about what is happening, you need to take multiple paths and try to figure out what's the best way to reach the target. So now, did we achieve our goal? In fact, yes. If you add up all these techniques, you add up prompts, you add database sensitivity, and now you add output token probabilities together, you can actually achieve the upper bound of 11.84 in this case. Okay, so, but still there is this elephant in the room. How do you know that what you are producing is not just high performance and incorrect rewrite, where the results will actually be different from the two queries on a database? So this is a hard problem. People have been struggling with this for the last 50 plus years. Okay? So even if you look at just basic relational algebra, and these are some landmark results in the 1970s itself, there is the famous Al Aho, Jeffrey Ullman paper in the Journal of the ACM 1979. Both of them, of course, as you would know, are Turing Award winners. It showed that the general case of query equivalence, especially when it has set difference, so whenever there's negation, things become very hard, is actually undecidable. Forget NP completeness, it's undecidable. And then there was the famous Ashok Chandra and Merlin paper in the Stock Conference of 1977, which said that even if you restrict your attention to just conjunctive, that is, select, project, join queries, even that is NP complete. Very depressing news. And now if you look at SQL, SQL goes far beyond basic relational algebra. Okay? It has correlated subqueries, aggregations, scalar functions, nested stored procedures, triggers, nulls, recursion, the whole shebang is there. Okay? Definitely undecidable. Okay? So you can't solve this problem. But can you do something to try to minimize the possibility of making a mistake before you, of course, give it to the DBA? So for that, there are two kinds of approaches you can take. One is to take the statistical approach, which is to say that, let me take the original query the user gave, let me take the rewritten query, and then try it on many different databases. Let's look at the results that come out. If any of them have a difference, then it means that your rewrite was wrong, because you got different results. Okay? This can be done for all query rewrites, and you can compare the results. The other approach, which can be done for a more limited scope of queries, is to actually use provable mathematical techniques. Okay? So there are a variety of tools which have actually gained currency over the last 5 or 6 years. One is to use logic-based tools. So there is a well-known one called QED, okay, which stands for Query Equivalence Demonstrator, which comes from UC Berkeley. Then there is an optimizer-based approach called the use plan, which comes from the Microsoft. Then there's a mutation-based technique, which some of you from IIT Bombay would probably be familiar with. Professor Sudarshan has this a project called Xdata, which has been working for probably the last 15 years or so. And they look at a mutation-based approach to try to decide whether two queries are different. I'll talk a little more about the next slide. This is from IIT Bombay. At IISc, we have been looking at behavior-based comparison of queries. There's a tool called Unmask in this respect that we have created. And we are also currently looking at rule-based transformations to check whether two queries are identical. So several of these approaches are currently ongoing. So let me just quickly walk you through them. The statistical approach is to say that just try the result matching on multiple databases. Notice that you could still have false positives. It's possible that on all the databases you got identical results, but there exists some other database on which they will not be identical. So for example, if you had written an inner join, when actually you should have written outer join, this will only show up if there are null values. Otherwise, you will not get the error. Okay? But now, if you say that let's do it on the original database, then you would have to wait for your grandchildren to be born before the answer comes back, because running it on a petabyte is no fun, and we have to do it multiple times. So we use sample databases, that is small versions of database. Now we think, okay, it's simple to do independent random sampling and take it. It actually doesn't work. Why? Because if you take random samples from the original database, it's very likely that the query will give you empty results, both the user query and the transform query. And I cannot compare in the empty space, saying that both gave empty is the same. You must have populated results. So to ensure that you get populated results even on the sample for the query, you need to use more sophisticated sampling techniques. For example, there is a technique called correlated sampling, which was proposed in Sigmod 2013. You can use that to ensure that there's integrity in the joins. What we have also done in addition is to add some masala. We change the filter constants in the query, because by changing the filter constants, you're not really changing the query semantics itself. So to ensure a populated result, we also insert synthetic tuples into the databases to ensure that you at least get some output and not just an empty hole. And of course, in the end, you can always try it on the entire database. So we used a lot of sampling techniques to try this out. What about the provable techniques? As I said, there has been a resurgence of interest in this field over the last decade. There is COSET, which came out in the CIDR conference, which Professor Michael Stonebraker had started several years ago. Then there's SQL Solver, which came out in Sigmod 23, QED, which is quite popular, and so on. In SQL Server, there's an interesting feature, and maybe some of you who are developers in Postgres here may also want to duplicate this here, is that there is something called the use plan feature, which is to say that I have the query here, and I tell the database system, please use this plan to execute the query. It might not like your choice, but it will go and do it. I'm saying that you are nuts, but I don't mind. If you give me this plan, I'll go and execute it here. So it's not the optimal plan, which it would itself have produced, hopefully. I'm giving you a foreign plan saying, please use this foreign plan for this query. So what it does in that process is to check whether the plan that you are giving is legal for that query or not, because it's possible that you might have made a mistake. So the first thing to check is, does this query get implemented in this plan? And there, the use plan feature comes in very handy, is that if it says, yes, this plan can be used for this query, then what we are doing is, we have the original query, and we have the rewritten one. We get the plan for the rewritten query, take that plan and give it to the original query. If you find that it says this is okay to use this plan, I don't like it, but it's still correct, then you know that it's equivalent. But there's a caveat here. It can only use plans that are within its search space. If it's coming from outside the search space, then all bets are off. It actually tells you that I don't know whether this is legal or not. Okay? The other approach that you could use is what is, as I said, in IIT Bombay is used, called Xdata. This was done by Professor Sudarshan. It's a brilliant problem. He had a large number of undergraduate students. They gave assignments, and every student wrote the SQL query in a different way. The TAs had a horrible time trying to figure out whether the queries were correct or not, because you can write it in a very convoluted manner, and invariably the student will disagree with the TA. So to fix this problem, what he said is, let's do an automated mechanism. And what he says is, let me create a small database, which is a small curated database, which is synthetic, such that if my query differs from your query, okay, so you assume that the instructor query by definition is correct. If the student query has a small difference between the instructor query and the student query, that database will produce different results on these two versions. So that's what he calls as the mutant version is. The student has the mutant version, you have the original, and you create a small database on which these two versions will produce different results. So we can use this technique again between the original query, the user query, and rewritten, create the small synthetic database and say, do you get the same answer on this or not? And the synthetic database is looking at the query and trying to find out ways to distinguish between them. Okay? So there's a lot of nice theory which has gone into it. The latest paper from Sudarshan's group is in Sigmod 2026, so if you attend the conference, you'll see that firsthand. And then we ourselves, as I said, have worked on this hidden query extraction problem, where you say that there's a black box. If I shake it, I know it's an SQL query. but I don't know what is inside. I have the object file. So I can run it on arbitrary databases, and I can look at the inputs and the outputs. So this is called as active learning in the machine learning community. So now we are looking at the behavior of the system, because you can't open the box. There is a opaque binary. So if you look at the behavior equivalence and bottom-up construction, you can check whether, although here it is not hidden, you actually have the original query and the rewritten query, to treat them as being hidden queries and say that there is just two object files. Let's see whether they produce the same extracted query or not. If they produce the same extracted query, then you know that these are identical. Okay? So this is on a behavior-based thing. So you can use this array of techniques, and to check the rewrite, if it's in scope, you can establish formally the equivalence. You don't have to invoke the DBA, but otherwise you can use the statistical test and finally give it to the DBA saying we have done a battery of tests and it looks like this is okay, but you can verify it for yourself in the end. Okay. Yeah, so now I'll just summarize by how does this all work on the entire TPC-DS benchmark, because we only saw the micro benchmark earlier. So the two rows that you see here are, one is LITHE and the other is the state of the art, which are other rule-based techniques, which I can discuss with you offline. So the second column there is number of PR, tells you the number of productive rewrites. And we're looking at productive, we mean that you're improving by at least 50%. Because if you say improve by 10%, 20%, people are not very impressed nowadays, because much of it may go away with some of the other coding and execution strategies. We are looking at minimum improvement of 50%. Out of the 99 queries with LITHE, 26, that's about 25%, you could improve by more than 50%, whereas the competitors could do about half of it. Then if you look at the optimizer cost speedups, it's an incredible 11.5, the geometric mean to on these 26 queries, the scale of improvement. And again, with the competition, you get about half of this. And you might say, okay, but we don't trust the optimizer cost estimates. Did it actually work? So that's the last column that you see, which is the time speedup. And there you see it's even higher. We have a geometric mean of 13 times. Okay, 13.2 compared to the original thing, just by doing rewriting of the query. Nothing, not touching the engine, not touching the optimizer, not touching storage module, nothing. Just saying that please take this version, replace it with this version, which is semantically identical, and you get a geometric mean speed up of 13.2. Okay. So, and also, although I didn't talk about regressions, we find that the current tools in the state of the art, the competing tools, they can often promise a lot and actually do much worse. So for example, one of the tools promised 100 times speed up, but actually slowed down by a factor of 2. Okay? We have techniques to ensure that this doesn't happen by using various kinds of first and second derivatives of the planned cost functions and so on. You can do interesting stuff here. Okay? Yeah. So to conclude, the basic message here is that with careful engineering and putting the right guardrails, our foundation models can actually be productively leveraged for something which has been a crucial optimization problem in our industrial and database systems for a long time. And what is interesting about the LLM is that it is not confined to a tunnel vision, because all the engines have a certain tunnel vision which has been developed historically. They're only looking at this silo. But it can bring in techniques from outside. So it can, for example, take the Postgres ideas and go and give it to SQL Server and say, ha, this is better than this. Okay? And most of you would agree with that. So it explores. So LLMs give you breadth. Database engines give you depth. So the power of the LLM is to say that steal your neighbor's idea and come and put it here. And you can do this cheaply. You can do this non-invasively. And you can do it very efficiently. So that's the kind of the USP here, is that you explore new regions that are outside the scope of the native system, and it delivers you much greater modeling power. And historically, if anybody wanted to create a new database system, we used to always tell them, think 3 times and then say no, because it's a huge effort. The engineering exercise is very large. And usually it was not because of the core engine, but because of the supporting modules like the query optimizer. It's a very large piece of code, takes enormous time to understand and to build and so on. But now you can get a quick and cheap mechanism via the foundation models to build a query optimizer, at least at the initial period. Later on, you may want to do your own system, but this gives you a good way to get up and running. So for startups, this is ideal. And you might also worry, okay, everybody loves this word agentic today. So we've also been recently working on the agentic pipeline for LITHE. So what I showed you was the bare bones version. You can now decouple reasoning from the rewriting, and this actually gives you better performance because it supports self-reflection and also improves reliability. Okay? Yeah, So with that, again, let me just remind you about the ACM Sigmod conference, first week of June. And this will be not at this Sheraton, but at the Sheraton Whitefield at the eastern end of the city, okay, because that has a very large convention center. If you also want to have papers there, the workshop track is still open. There are totally 11 workshops, out of which I think about 5 or 6 still have the deadlines coming up towards the second half of this month. So you can either write a new paper yourself or ask the LLM to write the paper for you, okay, very quickly, and write a good one, okay, and then send it in, and you can have a workshop paper very easily. And there's lots of interesting topics which I think you'll find to your interest there. Okay? Yeah, so with that, thank you again for your patient listening, and look forward to it.